Hello, my name is Melissa Buechlein, and I'm an engineer at Wood. I'm here today virtually to talk to you about a project that Wood completed with the EPA. Dr. Michelle Snyder is my coworker at Wood, and Dr. Chris Owen is with the EPA. Together, we examined the AERMOD NO2 chemistry options at a large airport. The specifics about this project and the project location are confidential, but I'll still be able to share enough of our work today that this talk will be pretty interesting. First, I want to cover some brief background into AERMOD before talking about the specifics of this project. I will go through the basic setup and assumptions that went into the modeling process, describe the processes behind AERMOD's chemistry methods before going into the conclusions and planned future work. AERMOD is the preferred regulatory model for most air quality near source applications and is required under the Clean Air Act. It is a steady state Gaussian model with lateral and vertical dispersion. The dispersion is based on meteorological conditions and surface characterizations. The model uses preprocessors to develop the meteorology inputs and surface data. The EPA is constantly working to improve and evaluate model performance for a variety of air emissions sources. The objective of this project was to evaluate NO to NO2 chemistry options in AERMOD to inform airport modeling best practices and ultimately for regulatory purposes. The model was simulated for 1 year with hourly output, and the one monitor location was located about 500 meters from the airport boundary. Throughout the analysis, only wind directions from the airport to the monitor were considered. Meteorological data was measured at the airport, and airport source emissions were estimated using the Aviation Environmental Design Tool, or AEDT. The figure on the left depicts the various sources that were included. The figure represents the annual average total emissions in grams per second for a given hour of day. Notice that emission rates vary drastically from source group to source group and hour to hour of the day. Also, there were trends throughout the year to simulate real air traffic. This table includes more information about each source. AERMOD has many different types of source types, but the sources were characterized by AEDT, describe most airport-related sources as area or area polygon source types. The number of sources describing each source type varies dramatically, as does the total emission in grams per year. Here you can see the total emission from a group varies by 2 orders of magnitude between the parking facility with the least emissions and the aircrafts at cruising height with the most emissions. However, we will see in later slides that just because a source group has a large emission rate, that does not mean that the modeled concentration from that source group will be equally large, since we are only looking at concentrations that make it to the monitor location and height. Before investigating the chemistry options, we did an initial model simulation of just NOx emissions without chemistry. Those results are shown in the figure on the right. As you can see, runway makes up the largest concentration of NOx at the monitor, despite not having the largest emission rate, since concentrations are modeled at ground elevation. The figure also depicts 2 clear peaks in the concentrations, one in the morning hours and one in the evenings, when most airports are the most active. Remember that here and throughout the presentation, the results are queried to just the wind directions from the airport to the monitor. After this initial investigation, we moved on to examine NO2 chemistry options. AERMOD has 5 chemistry options for NO to NO2, and the 5 methods are ARM2, OLM, PV, MRM, TTRM, and GRSM. And on the following slides, I'll go into a little bit more detail about each of these methods. The first chemistry option we examined was the ARM2 option. It is one of the methods approved for regulatory purposes. The ARM2 method estimates NO to NO2 conversion based on an empirically derived relationship between NOx and NO2 concentrations from varied locations throughout the United States. So it is not specific to just airports. However, ratios have been developed for each different source type. The ambient ratio is a user input with a minimum value that we used of 0.186 and a maximum ratio of 0.717. The results from this method are shown on the right with a scatter plot. In this scatter plot, each model output was paired in space and time with the monitor NO2 measured concentration. The color depicts the PG stability class, where the cooler colors are more convective and the warmer colors are more stable. The wind directions are shown by shape. The blue solid line is the 1-to-1 line, while the dotted blue line represents the factor of 2 comparison. The red line is the linear regression, and although there's a lot of noise in the data, ideally the results would have a 1-to-1 ratio, causing the red line to overlap the blue solid line. The scale on each of the coming figures is different, so I identified the maximum concentration here of 90.1 ppb, which is of the same order of magnitude as the monitor concentrations. The next method we examined is the ozone limiting method, or OLM. It is also a regulatory method, and it converts all NO to NO2 based on a mixing ratio provided ozone concentrations. For this method, background ozone concentrations and NO2 to NOx and stacked ratios are required. The same style of scatter plot is shown here, but the axis ranges are different. Here, the max modeled concentration is 176 ppb, over twice the maximum concentration at the monitor. The third method we examined is the plume volume molar ratio method, or PV-MRM, and it is similar to the last method, only the NO to NO2 conversion is determined based on the volume of ozone within the plume between the source and the receptor. Here, the maximum concentration is 319.3 ppb, which is over 3 times the monitor concentrations. The fourth method we looked into is time travel reaction method, TTRM. This is a newer method and is not approved for regulatory purposes yet. It's still in the testing phases, so it requires an alpha flag. It's very similar to PV-MRM, and the results also look very, very similar. The difference between PV-MRM and TTRM is that the TTRM method includes time travel between the source and the receptor, but because our source and our receptor are so close, that's probably why PV-MRM is very similar to TTRM. The final method we looked into was the generic reaction set method, or GRSM. This is also a non-regulatory model option, and it computes NO to NO2 based on the equilibrium chemistry between NO, NO2, and the reaction with ozone. So in this instance, the maximum concentration was 191.2 ppb, which is higher than most of the monitor locations, but we're at least getting a little bit closer than with PVMRM and TTRM. This method requires the background ozone concentration, the NO2 to NOx in-stack ratio, and additionally background NOx concentrations. In order to look at how well the model predicted airport emissions, we did a shootout of a variety of statistics as shown in this table. In this table, I bolded each statistic that represents a more ideal performance when compared to the benchmark monitor concentration. For instance, the AERMOD method resulted in a mean concentration closest to the mean of the monitor concentrations. However, OLM and TTRM provided less model bias. The statistics shown in this table were calculated without the background ambient NO2 concentration added back into the data, but the model tended to overpredict concentrations at this one monitor location. And as you can see from the variety of statistics shown, there is no clear winner, indicating that the chemistry option alone does not tell the whole story. Which is why, in this sensitivity analysis, we also investigated the impact of modifying source parameters. We have an upcoming publication that will describe this work in much more detail. During that portion of the project, we investigated changing source release height, initial vertical dispersion, and source widths, in addition to converting area source types into another source type. Each source type in AERMOD uses a slightly different algorithm to estimate concentrations, which is why we investigated the model sensitivity to source type. Additionally, we intend to apply what we learned at this airport to other airports in the near future to gain a better understanding of how to best apply AERMOD model concentrations to estimate airport concentrations. To conclude today's presentation, I wanted to spoil a bit of the source sensitivity analysis work. On this slide, I've shown the AERMOD and GRSM chemistry options as in the same way as I did on the previous slides. Remember the axes maximum concentrations are different. The AERMOD maximum concentration was about 90 ppb, while the maximum concentration for GRSM was 190 ppb. However, when we modified the source parameters with information based on a combination of recommendations in the LiDAR report with initial plume rise and in the roadway hotspot guidance, the model estimated monitor concentrations much more closely. In this model run, we varied the taxi, roadway, and aircrafts taking off and landing source groups. The maximum concentration on that final figure is about 153 ppb. I look forward to applying the findings from this airport to future airports as we continue to work with EPA to identify recommendations for airport quality estimates. Thank you for your time today. Normally I would take questions at this point, but due to the virtual platform, I would encourage you to email me instead at melissa.buechlein@woodplc.com. And thank you.